Today, we're starting chapter 6 after we go over the homework. And then when we get back, Tuesday after vacation, finish chapter 6, which is 2 weeks from today, right? Thursday after we get back. Does that make sense? All right, where are we going here? Ready? Here we go. Transportation, here it is. If you end up liking this particular chapter, a lot of these are logistics jobs. Tell me you've heard of logistics. Logistics. Now, I remember being at this job in Ohio. This is way back in the 1980s. And the company I was with, our teaching industries, we manufactured bathroom fixtures and everything in the bathroom you can imagine. Bathtubs, tub surrounds, faucets, shower heads, vanity sinks, and of course, the toilet. We had a china shop, and it was making ceramic toilets, and our whole philosophy as a manufacturer was the good, better, best marketing philosophy for every line of product. Does everybody know what I'm talking about, the good, better, best? Does everybody know? Really? What's the deal? You had to have had a marketing class by now, right? Anybody?
I've been one.
Seriously, you never heard of good, better, best?
Oh, yeah.
Many manufacturers, especially in the 80s and 90s, always had, we're making 3 of everything. One's going to be our lowest price point to get us in the door. Then there's the better, which we have a little higher margin on, and it has some better features, but it really doesn't cost us that much more to make from a manufacturing standpoint. And then we have the best, low profile, elongated seat, one-piece unit. Doesn't cost us, it costs us a little more to make, but we increase the price to the point to where we want to sell as many of those as possible because of the margin. It's all about the percent, not the, yeah, we make $10 off that, $5 off that. What is the margin we're making compared to the cost of making it? We want the biggest margin. Working not as hard for more money. Get it? All right, so it's the margin. So good, better, best has always been a philosophy for many companies and their products. What I'm getting at is, our logistics was not even a word yet. Wasn't even invented. But I had, learned about a lot of companies, and not a lot of companies had enough shipping that they would do themselves to have a person that would schedule the shipping. And that's what logistics is lining up all the distribution of your goods in order to keep your distribution costs as low as possible. Instead of just winging it. Hey, we got a shipment going here, a shipment going there, and everybody, I'll take it. Wait a minute. What's going to be the least expensive way for us to get these goods shipped? And that's where logistics came in. The company Artesian had somebody. She was great. We didn't call her logistics. I don't remember what the position title was, but where she was golden. And you got to remember this. When you get a logistics job, by the way, great experience. Good entry-level job for a business major in supply chain management, for example. Get your feet wet as to how things work in business. But her real success was because we owned our own trucks, so we had to schedule our own distribution. We had all our own semis. And where she made her money is, nobody was doing this, is that during the downtime where she had some free time, she was calling out near our customers in other parts of the country to try to find companies who need to ship things back to Ohio. We were in Ohio, Mansfield, Ohio. And so that was the big payoff. A bunch of companies back then would bring their trucks back empty. And all that cost involved. Where she was having our truckers pick up loads on the way that had to get to Ohio, and they had to come back and go right past those exits anyway, bringing stuff back. Sure, they're not right back right away. They had to drop some things off, but we're making some money on it, which was huge. So that was a big deal. And from there, many companies, obviously, I had not seen too many, but this one wasn't that big of a company, other than it owned its own trucks. But this is what this does. Transportation model says use math, taking into consideration the cost to deliver to all your customers and where you're delivering from, and all the costs involved, and take all your orders each period when you're ready to do deliveries and figure out what the least expensive way is to get these things delivered. So, here's the process for transportation. Let me start here. These are called nodes. And these are called arcs. Now, what I want to make sure you have in your notes, this is going to, on the quiz, it will make this problem so much easier. I'm giving you shortcuts that you can't find in the book. You ready? If you realize every single node is a constraint, then you can easily tell me how many constraints of this problem is supposed to have. No, every node. Every node. 5. 5 constraints. So you know, hey, here's a transportation problem, write a linear programming model. You know there's got to be 5 constraints involved. These arcs, each arc represents a variable. How many decision variables do you see in this problem? 6. There's 6 arcs. Everybody get it? Every arc is a variable. Every node is a constraint. It should be easy to answer the question, how many decision variables there are, how many constraints there should be. Okay? Now, to keep us all on the same page on variables, you don't have to do this, but this makes it a lot easier. If you number the nodes 1 through however many you have here, and 1 through however many on the right, for transportation only, not only, but transportation, it's not always this way for all of them, then the variable that represents this arc would be x1 to 1, meaning x1, 1, the first number is always where you're shipping from, the second number is where you're shipping to. x1, 1, x1, 2, x1, 3, x2, 1, x2, 2, x2, 3. This drawing represents that we have 2 locations we can ship from. Maybe they're 2 distribution centers, maybe they're 2 manufacturing warehouses. We have 2 locations. And we're about to schedule shipping, and we have 3 orders. Now this is very micro. We only have 3 orders that have to be delivered this week. This on the left is how many maximum are available to be shipped, supply amount. There should always be a number on the outside here representing how many could be shipped from these locations. Over here represents demand, which is how many each of these customers ordered. Now, I try to emphasize this anytime we talk about customer orders. Demand, we have to do everything we can to make sure demand is met. And these constraints should be equal signs, not less than equal, not greater than equal. We want to deliver exactly what was ordered from our customers. So this is going to be equal, the right-hand side is however many they ordered. Equal, however many they ordered. Equal, however many they ordered. Everybody get the right-hand side of these constraints? Over here, these 2 constraints are almost always, unless there's a special story involved, less than equal, because even though we have a whole bunch here to deliver, we don't have to ship all of it. We can keep some for the following deliveries. But we have to ship enough to meet the demand. This is less than equal. The right-hand side is however many are available from that location. Less than equal, however many are available for that location. Now, are you ready? The variables used in any of these transportation constraints, the number of variables is however many arcs are touching the node for that constraint. Customer number 2, how many variables would be in that constraint for customer number 2? 2. This is customer number 2. This is warehouse number 2. Customer number 2 only has 2 arcs touching it, so there will be 2 variables in that constraint equal to whatever the amount ordered. Everybody hear this? I am giving you the most unbelievable shortcuts to these transportation problems to make them so easy. Those who are not here today, I hope they're watching this video, because you're not going to get this on your own. I don't think it's in the text. Are you ready? These 2 arcs equal this. What is this arc? Give me this variable right there for that arc. x1, 2, call it 12, I guess if you want, but x from 1 to 2, plus x, no,
2 to 2.
x2, 2 equals whatever that number is. Get it? All right, let's talk about this one. The left-hand side would be, the variables involved would be, this variable would, for this arc would be what?
Z21.
Now forget the C.
21.
x21 plus, what's this one?
X22.
Plus x.
X23.
Equal, less than equal, whatever that number is. That's how these are written. You could write any one of these now, right?
Yes.
All right. Now, here's where everybody blows it. These numbers represent the cost for every unit going from this supply location to that customer. That's the cost for X11. That's the cost per unit of X12. The decision, do you see what the decisions are? You have to decide how many are being shipped from our first warehouse location, whatever it may be, to each of the customers. Your other decision is how many will be shipped from here to each of the customers. How many decisions do you see? 6. Each arc is a variable, which is a decision. 6 arcs, 6 variables, 6 decisions to be made is how many each of these. There's your cost. Now, this is what you got to write down. In transportation, these cost numbers are never in the constraints. Let me repeat that. This is where everybody accidentally puts them. These costs on these arcs are never, those numbers of costs are never in the constraints. They're only in the objective function. Everybody hear it? These costs that are on these arcs are never part of the constraints. They're always represented in the objective function. And it makes it so much easier because you're going to have one where it says, write the objective function. Write the constraint for customer number 2. Write the constraint for supply node number 2. And if you have these little rules down, and a lot of these rules I'm telling you for transportation, you're going to find out that most of them apply to transshipment. Most of them apply to assignment. Most of them are going to apply next week, after a break, to shortest route. And that last one, max flow, I think is the last one, right? We have 5 in this chapter. So when you're looking at a question on your next quiz and on your final, that you go, oh, this is a network model. It's got arcs, it's got nodes, it's got something being delivered or something like that. The challenge is, now is this problem transportation, or is it transshipment, or is it assignment, or is it shortest route, or is it max flow? And that if you're studying to prepare for this chapter for the quiz or final, it's taking random problems, saying, identifying which one you're going to use. And then grab those little rules I gave you, and it will make it so much easier. Just go, okay, each node's a constraint. So I must have 5 constraints here. And the right-hand side would be equal, and the other ones would be less than equal, and so on. Get it? It's identifying which one to use. So, let's go to this first example, so you can see how this is used. This company makes concrete blocks. They got orders for 80 tons of it that we got to figure out how to deliver. The 3 locations, this is, would we make these at these locations? Or is this our customers? This is our customers' orders. Northwood customer, they want 25 tons. Westwood wants 45 tons. Eastwood wants 10 tons. 3 customers. If I asked you to draw this as a network model, where would these nodes be represented, on the left or right? That's right. And how many nodes would you have on the left?
3.
Got it. 1, 2, 3. There is the customers that we have to provide this concrete block for. Our company, us, we have 2 plants. Each of the plants are producing 50 tons a week, and this is a weekly order. And we can deliver from either plant. Let me just add that to it. Now, where are these plants represented on this network? On the left side, how many locations are there? 2. We can ship from either one of these locations, but if we ship from this top location, what's the maximum we have available to ship? 50 tons. What about this location? What's the max? Also 50 tons. Let's get to our orders of our customer. This is Northwood. 25 tons? 25 tons. This is Westwood, which is 45 tons. Eastwood is how many? 10 tons. Is that it right there? What is this right here? This is our...
It doesn't say...
Doesn't matter.
Just say X1.
Let's turn these into numbers. What number would this be?
1, 2, 2, 3.
All right. Now, how we know which supplies could ship to which customers, you'll always get a cost grid. And a cost grid, if plant 1 cannot ship to Northwood, either this would be blank right here or a 0. If there's a number there, it's trying to say, yes, we can ship from Plant 1 to Northwood, and for every unit, which in this case is a ton, it's gonna be $24. So however many you're gonna schedule from Plant 1 to Northwood, here we go, we gotta put 24 as a cost on top. Now, is this 24 gonna be used in the constraint related to the supply or the demand? What? Good job. That's right. That was a trick question, just to see if you guys are all with me still. Yeah, this number 25 is never used in the constraint. So it wouldn't be a constraint for this one or this customer, because it's not in the constraint. You gotta get that through you. Those are one of those ones where I try to push it through because I don't want that mistake to be made, and yet always, I can't get it through, and there's always still someone making that mistake. I don't want you guys to be fooled into thinking these costs are part of the objective, or part of the constraints, because they're not. Let's do the rest. My question for you is, can both locations ship to any one of our 3 customers?
Yes.
Let's put them on. Here we go, 24, give me a cost, 1 to 30, 40, this pen is running out. This one goes up here, this one goes here, this one goes here. What's our number? 24, 20, 30, 30, 40, 42. All right, we're there? You ready? Ready? Constraint number 1. We're going to do supply number 1. Let's start with the right-hand side. Blanky blank 50. Can't hear you. Huh? Come on, this is... Had to be one or the other. Less than equal 50. Now, how many variables are going to be on the left side?
3.
Because why? Because there's 3 arcs touching. Let's name those 3 arcs right now. Here we go. X.
24.
Plus X.
30.
Come on, stop. X. 1, 2 plus X. 1, 3. That's it. Never put those costs in there at 3s. Listen to me? All right? Never. Let's do customer number 1. What's the right-hand side? Equals 25. How many arcs are touching that node? 2. Give me the arcs. X. 1
plus X2.
Come on, X. 1 plus X.
2 1.
2 1. Very good. 1 1's going there and 2 1's going there. Those are the 2 variables. Equals 25. Do you see the logic though? Like now I'm going to pick a random one. I truly want you to tell me what it should be. I want to make sure everybody sees this logic because these other ones are done exactly like these are, the same exact logic. Then we'll get to the objective.
Since you're going back to this way, can you write it like 1, 2, since you're going
No. This order of numbers they mean where it's coming from to where it's going to. If you switch that to 2 1, it's going.
Some of the equals. Yeah, the equals, since it's going back this way. Like,
So what do you want to switch here?
I'm saying, like, can you, can you do it as 1, 2, rather than 2, 1? Like, since
No. 1 2 would be right here, which has nothing to do with that.
Okay.
It has to be. These numbers have to be in the order of where it's coming from and where it's going to.
Okay, so
It has to be.
Okay.
Because if you switch them, it would have such a different meaning that 2 1. I'm sorry, 1 2 is not touching that. It wouldn't even be in this particular constraint. Let's try another one though, you guys. You ready? Customer number 3. Give me how many variables are there in customer number 3? 2, which happen to be X. Come on, right here. 1 3 plus X. 2 3 equals 10. These are too easy.
What was that for?
That was this one right here. X1 3 plus X2 3 equals 10. Now, how many constraints, if we did them all, how many would you have? 5 constraints. How many variables in the objective function? 6 variables. Now this is where you do it. I got the camera pointed so we can get this in here, but let's get a pen that's darker. You guys are going to see it. What are the chances? You ready? Max or min? Can't hear you. Min. All right. Let's give me the first variable.
X11.
X11. More to it.
Plus.
No. 24 x11 plus 30 x12 plus 40 x13 plus 30 x21 plus 40 x plus 42x. There's your objective function. This problem's done, except for solving it. You've got to make sure to have a constraint for each node. You got to make sure the variables for each constraint or however many arcs that are touching that node. You got to make sure that you don't put the cost inside of here. When you read the story, you're probably going to be asked to draw a network, and the most common mistake is accidentally leaving the numbers off on the outside. You got to have the 50-50 and 25-45-10 as part of this drawing. Having your costs on the arcs. All right? And then this leads you to making these constraints so easy. I think I posted this concrete right here. Hang on, let me get this so you can see it better. Now look at how different this looks than what you're used to before this. By the way, I think there's assistance on pages 313, 315, because this is a little different than you're used to. What's happening here on these network models is that over here is an example of the supply, the demand, or the supply. Here's an example of demand, customers. Over here, each plant can supply up to 50 tons. Each customer's order, 25, 45, 10. Here is the minimization. Now down here, right here where these zeros are, is where the optimal solution is going to be. Now when you're doing solver, you have to tell these are the cells where you want the optimal solution. And what's happening here is that it's taking each one of these cells times its corresponding cost and then adding them together. Whatever this is times 24 plus whatever this is times 30 plus whatever this is times 40 and so on for all of these. When these add up, this will be the total amount being shipped to Northwood from both plants, which better equal 25 because they ordered 25. This will represent what's being shipped from each plant to Westwood and Eastwood. And they've got to equal that. We're telling the constraints, when you enter the constraints, we're telling it that this cell, and this cell need to be equal to this cell, and this cell if you combine them. Or I could say this equals this. Next constraint, this equals this. Next constraint, this equals this. Next constraint, this is our supply. Wherever it's going to our customers coming from plant 1, there's the total, must be less than equal to 50. There's a constraint. However, from plant 2, there's the total, less than equal. So when we have 1, 2, 3, 4, 5 constraints, when you enter that in, let me show you how that's done. So we're going data, solver. It's already there. There's our objective function. That's just like we've done all this time, every other problem, right there with that cell location that's being calculated. This is a minimization problem. Now, your optimal solution is right here, F19, all the way to the bottom right hand. I gotta make sure. Yeah, right here is H20. So it's these 6 cells. Excuse me. Here's our 6 decisions right here. These are the totals, these bottom ones. Here's our constraints. Should say F21 equal to F23, or they're combined. F21 through H21 equals F23 through H23. And then our less than equal constraints. This cell and this cell less than those 2 cells. See how it's all entered in there? If I open this up and that's there, that means that this one that's posted has all that information in there for you so you can see how it's done. What will happen is if you have a problem that has 4 customers, you're going to add a column here, which will add it here. You're going to add the customer name. You're going to add the numbers. You're going to put that there. This is all going to scoot over. That's all that's going to happen. You can reuse this over and over again for any of these network models because they are done differently than the other one. See, you're entering all this data up here. If you look down here, every one of these cells, again. Okay, every one of these cells right here, this is adding these two. This one's adding these two. This Northwood is just copying whatever you typed up there in F6. If you type Northwood, it shows up Northwood. You type Westwood, it shows up Westwood. This is all, this right here is just whatever's typed there. This is looking at that stuff. So all of this down here, you don't need to change because when you change the numbers and the names up here, it will all change down here automatically. Okay, let's solve it. Data, solver. We got the, uh-oh, what happened there? How did these disappear? Right here, right here. Right? Everything else look okay? Okay, here we go. How many are we, hey, how many are we?
That's the wrong sheet.
Oh, that's a lot of cement.
How many are we shipping from our first to our WW customer, our second customer, from our first warehouse where we manufacture it to our second customer, Westwood?
45.
45 tons, right there. Plant 1, right there. Is Westwood going to get all 45 tons? I guess so, so we just saw it. Is Northwood going to get all 25 tons?
No.
All together?
Oh, yeah, yes.
Yes. 5 of it from plant 1, 20 from plant 2, right? And then Eastwood is getting all 20, no 10, and it's all coming from plant 2. Our plant 1 and plant 2, these node constraints, are they both binding?
No.
They're not? Which one's not binding, plant 1 or plant 2? Plant 2. Plant 1 is shipping all 50. So there's no difference because there was 50 available. Plant 2 only has to ship 30. You have 20 left over for the following week, which is the difference here. Slack, because we knew it was less than equal, the difference is 20. By the way, the slack right there is all that's doing is it's looking back here, which you'll have to manually enter this, and determining if it's less than equal, it knows to put the word slack. If it's not, it's going to put blank. I thought I had programmed it to put surplus. Anyway, so don't use that. All right, so there it is. We got it? You ready? Let's do another example. Now, let's go to transshipment. By the way, you can do any transportation now. What's going to change is how many nodes, how many arcs. It's all going to change.
Okay, so if we were to enter like another column while we were doing it, it would change the whole everything on the right, like the slack, surplus side, all that, and we would have to change
It changes it, yeah, but there's still some formulas you got to go in and change because you added a column.
Okay.
You guys hear what she was asking? She's saying, what if we, let me just add a column here. Well, let's go to the right or left, I don't know, but let me go insert, whoops, home, insert, column, right there, went to the right. So I'm calling this one blah, blah, blah. I'm calling this blah, blah, oops, blah, blah, and blah, blah. All right? We better increase our demand. Anyway, down here, I'm just going to copy and paste, and then we'll put, no. Did I put dollar sign? Oh, what's going on here? Okay, this equals H6. This wasn't supposed to take so long. Now, what she's asking is, did these formulas over here change? For example, is this adding now all 4 instead of only the 3? And sure enough, F19 to I19, it's adding all 4. So by adding a column, it went ahead and added a letter to this.
Okay.
And then so this one will also be from F20 to I20. So it's counting all 4. What else would change? So that's about the biggest change right there, right?
We wouldn't be able to meet the order because it's over.
No, yeah, it's too many, I know. I'd have to increase supply. I was just showing her that the formulas will change automatically.
Okay.
And you would have to manually put the formula right there.
The equal.
It equals this one down here, A.
Okay.
Okay, you ready? Transshipment. I'm skipping assignment for now. Let's go to transshipment. Come on. There we go. There we go. Stop it.
Why?
Just give me 5 minutes and you'll realize just how easy this is.
You said 5 days?
Minutes. Minutes. All I need is 5 minutes. You ready?
Sure.
You ready? This right here, just like transportation, supply. Supply. Whatever's on the outside, what do you think the right-hand side of these constraints would be? Less than equal, greater than equal, equal? Less than equal, supply. Over here is our customers with demand. The constraints for these, the right-hand side would be equal, just like transportation. Every node is a constraint. Every arc is a variable. The difference here is you can't go 1, 2, 1, 2, 3, 1, 2. You got to make sure every node has a different number. Because this arc is represented by the variable x1, 3. If this were x1, 1, and then you got another one here, you'd go x1, 1 could be this arc, or 1, 1 could be that arc. It doesn't make sense. You can't have two 1, 1s. So on transshipment, it's the only one that out of the 3 that we're studying today, you got to make sure every node has a different number to represent the variables. Every variable, every arc is a variable. So you see how many variables are involved, correct? Transportation, exactly the same. Here's the difference. Transshipment is when you're reading a problem and the story says it's being shipped from somewhere, it's got to get to our customers, but it's being dropped off somewhere. Most of the stories are distribution centers where it gets split up and then ships back out to the customers. And so, here's the difference. These are also constraints, just like these, but the middle constraints, whatever goes into a distribution center, heads right back out, so these are all equal to 0. Let me repeat this. On transshipment, the middle nodes are always equal to 0, which means whatever goes in goes back out. Nothing gets left in there. It heads to our customers eventually, coming from supply. This is how many we can ship. This is how many is going to be delivered. And this is where it's going to go to be split up before it heads back out. Walmart, distribution centers all over the place. If you ever take road trips on the highway, a lot of them are near the highway. You can see a big warehouse. They got a Walmart kind of hidden on the side, but you see a bunch of Walmart trucks sitting outside of it because they come and deliver. Things get split up. The trucks head out their separate directions to the stores then.
Amazon too.
So this is a perfect example. Now, you can write this constraint because it's no different than transportation. You already told me the right-hand side would be what? Less than equal to whatever that amount is, right? How many variables would be related to this constraint? 3. X, 2, 3, X, 2, 4, X, 2, 5, less than equal to whatever that is, right? You could do this one. No different than transportation. Equals how many variables? X, 3, 7, X plus X 4, 7 plus X 5, 7 equals that. You're almost done. Am I 5 minutes up, Justin?
No.
Okay, you ready? These all equal 0. And you have how many arcs touching this node? 4. But since it equals 0, you got to make the arcs coming or going from one direction positive and the arcs going the other direction negative. And it doesn't matter what you choose, but you've got to be consistent with every middle node when you write these constraints. So if you make these negative and those positive, these have to be negative, positive, negative, positive. You must have consistency, whichever you choose, though, to go. Let's make these positive. I'm going to write this down, so you need to visualize this. You ready? I'm going on the top one. X, I got to look here, X 1, 3 plus X 2, 3 minus X 3, 6 minus X 3, 7 equals 0. There it is. Now Justin's, now my 5 minutes rule is up. He's going to tell me this one. Are you ready? Stop. You ready? Ready? Hit me with this one. X
1, 5,
plus X.
2, 5.
Then what?
Minus
Minus X
5, 6.
minus X
5, 7.
equals.
0.
Is that easy? Is that easy? What looked hard, does it look easy now?
Yeah.
Let's do the objective function. All right? Let's do the objective function. The objective function is no different than transportation. There's no negatives involved. The only place you're doing something different using negatives are just these node constraints. So in this case, you'd have 7 constraints. Now, the objective function, if you think since this is transportation, but it just has these distribution centers in the middle. Do you think this is a minimize or a max? It is a min, no different in transportation. And it's going to be min this cost x13 times that, plus this number times x14, plus this number times x15, plus. Just like transportation, no different. Easy? We're good? Want to see the example? Here we go. All right. We, just for a hint here, we're the distribution center. We're represented by the middle nodes. Okay? As we read this, I want to make sure you realize that. We are the middle nodes. This is us. We have a north side and a south side facility, and we supply these three firms that put some orders in with customized shelving for their offices. We do a ton of shelving business. And we have 3 orders in. We have 2 locations, okay? This is us. They both order shelving from the same 2 manufacturers, which are Arnold Manufacturing and Super Shelf. This is who we get the shelves from, the manufacturers. They send it to us. We do our little thing to them, and then we take them, we customize them, then we take them to our customers and install them. We're the middle. Everybody with me so far?
Yeah.
So if we were drawing this network, how many nodes would be in the middle?
3.
That's right, because we have a northern location and a southern location, and we're the middle. Right here, right here. What about the left side, the supply of where this is all coming from? How many?
2.
2. Just Super Shell, what are they called? Arnold and Super Shell. Arnold and Super Shell. And then, how many customers have orders in we got to get these shelves to? 3. Okay, are you ready? When we get to a slide that gives us the numbers, we'll know if each of these manufacturers will deliver to either one of our locations or not. And we'll know if either one of our locations can provide these shelves to all 3 of these customers or not. Again, if you see a 0 or blank, it means it cannot go from this to that. You ready? Meanwhile, what do I put here for a number? Just a number. 1, 2,
3.
Very good.
5.
Very good.
6.
Very good. How many constraints are there going to be? Everybody knows a constraint. Currently, weekly demands by the users are Xerox wants 50. What number nodes Xerox?
5.
And then Hughes wants 60. Rockwright wants 40. Where's the 60 go? This is 40? Is that right? There's our demand. What about Super Shelf? Both Arnold and Super Shelf said right now we can ship out 75. And the other company said 75. Where does that go? There you go. There you go. All right. All we need to know now is can anywhere be shipped to anywhere and what the cost is going to be. Here we go. Can both manufacturers ship to either one of our locations?
Yes.
Let's get arrows. Here we go. What's the cost going from, number 1 is Arnold, right? We'll put an A for Arnold. This is S for Super Shell. Thank you. Arnold will cost how much if we have to ship to our northern location? $5 each, and the other one? 7. What about going from Super Shelf to our northern location?
8.
Is it 8?
No.
And the bottom one?
4.
4. All right.
Wait.
No, it's not. It's 5 and 8 on the top one, and then 7 and 4 because you have.
Hey, man.
Yeah.
Is that Justin?
No.
Okay. Is this supposed to be an 8?
Yes.
Yes.
And this is supposed to be
7.
7, 4? Okay. We're there?
Yes.
All right. Can each of our locations deliver these shelves to any customer at all?
Yes.
They can? So I got arrows going all over?
Yeah.
Here we go. Here we go. Here we go. Give me these 3 costs.
1,
1,
5,
5,
8,
8. Here we go. Here we go. Here we go. Give me these. 3, 4.
4.
How many variables are there going to be?
10.
10. Don't forget, every arc is a variable. So when I write the objective function, how many variables are going to be in it? Yeah, every arc is a variable. Let me just start the min or max. Min,
It's going to be X.
5, x 1, 3 plus, then 8?
8.
8, x 1, 4, Every one of these costs with the variable, where it's coming from, where it's going to. All right? Now let's do a supply node constraint. Let's start with the right-hand side. Constraint number 2, coming from super shelf. What's the right-hand side going to be? Less than equal, greater than equal, or equal? Less than equal what? 75. We can order all 75 that super shelf said they have, or we may not need them all, right? We don't have to take them all. The left-hand side would be the variables touching that node, which is how many variables? 2. They happen to be, what is this, 7x2, 3?
No.
Just checking. x2, 3 plus x2, 4 less than equals 75. There's these two arcs do not include the cost in the constraint. Less than equals 75. Let's do this customer's constraint. Right? They ordered 50. Equal, less than, greater than? Equals 50. How many arcs do you see touching that customer? 2, which happen to be x
3, 1.
3, 5, darn it, plus x 4, 5 equals 50. Get it? You can do any of these. Now let's do a center node. Are you ready?
Yes.
Let's do the top one. What's the? We got enough room here. What's the right-hand side of this center node? Whoa, man, what is this? Let's give it away. All right, here we go. Let's go right here. Equals 0. How many arcs do you see touching that one? No.
Or sorry, 4.
No.
5.
5.
Oh, yeah, that's 5.
2 going in, 3 going out, right? Here we go. I'm just going to jump in here because we got another one. It is? Is that true? Check here. Here we go. x1, 3 plus x2, 3 minus x3, 5 minus x3, 6 minus x3, 7 equals 0. Is that right?
Yeah.
Now, I just want to make sure you understood what I meant earlier. This could be negative x1, 3 minus x2, 3 plus x3, 5 plus x3, 6 plus x3, 7 equals 0. That's also correct as long as you're consistent with all the other middle nodes as to which ones are positive, which ones are negative, coming or going. You've got to be consistent. That's the key. Okay? You see how easy these are? Did we do the objective function? So we're done with transition it? Well, let's solve it. And wait, we don't have to solve it. My question for you is, how many are we getting from super shelf to our northern location? How many are we getting? I got to look here. From super shelf, which is 2, to our northern location, which is 3.
0.
How many?
0.
That's right. From super shelf to our northern location is 0. How many are we getting from super shelf altogether? All 75. Where are they being delivered? X2. X2 is going to 4, all 75 to our southern location. Our southern location, are they going to end up delivering it all to, I don't remember who this is. Shoot.
That'd be Rockaway.
So is our southern location delivering any, or how many are they delivering to Rockaway?
40.
X4, 7, 40 of the shelves coming from this location there. So, Mike, now, we're trying to keep our costs for all these 150 shelves, is that right? All 75 from each of the Arnold 2? We're trying to keep these costs as low as possible, going to our customers, going through each of our locations after we customize them. What is our total cost for this whole order? $1,150, and there's no way to get that cost any lower. That's as low as you can get it, even though there may be a different way of delivering these and which location. Doesn't matter. That's as low as you're going to get the cost. So you might as well put the order in, 75 from each of them, where you want them delivered, get each of our locations ready, and make sure they realize where these deliveries are going to. Our northern location is going to be delivering 50 to the first customer, and 25 to the second customer, and none to the last customer, because they're getting it from our southern location. Get it? So it's not just doing these, it's interpreting the output also, which you know is going to be in your future. What do we got? Assignment? Is that what we got? Or spring break? What? Stop. What? Alex, I've seen you look up. Are you ready? Are you guys ready? All right, spring break. Good to see you in a week or so. No, more than a week. Week and a half.